So, okay. So today we're listening to César Ceballos from Graz, right? And he will be talking about Hopf algebras and diagonal harmonics. So please, César.
Thank you very much for the invitation. So as you said, I will be talking about Hopf algebras and diagonal harmonics. And this is based on joint work with Dieudonné and Vincent Pilot. Okay, so let's start. So my idea for the talk is to present some insight into two apparently unrelated areas. Namely, first, the theory of Hopf algebras, which is motivated by work of Hopf on algebraic topology and of Dieudonné on algebraic groups from the 1940s and 50s. And second, the theory of diagonal harmonics, which is a little bit more recent. So this was initiated by Garsia and Haiman in the early 90s in order to understand properties of Macdonald polynomials. And the main objective will be to present some connections among these two areas. And in order to do so, we will need certain combinatorial objects. And these objects are called pipe dreams. Okay. So before I tell you a little bit about Hopf algebras and diagonal harmonics, I will tell you a bit about pipe dreams. So a pipe dream is a combinatorial object that looks like this. So it's a triangular array, which you get by filling some boxes in this triangular shape with crosses and elbows, so that they satisfy some properties. So the first one is that the pipes or the lines entering on the left exit on the top. And the second important condition is that two lines cross at most once. Okay, so they cannot cross two times. And for the purpose of this talk, we will also assume that this top left corner is an elbow. Okay. Now, these objects were originally defined by Bergeron and Villay in this form, and they call them RC graphs. And they did it based on work on Fomin and Kirillov from the 1990s. And then these objects were renamed after work of Knudsen and Miller, who revisited them in the 2000s or 2005 in the study of Brommer geometry of Schubert polynomials, and they renamed them as pipe dreams. And the reason why they are called pipe dreams is because they have a nice similarity with this video game called Pipe Dream, where you are supposed to build some pipes to guide some liquid that is coming from a source. Okay. Now, why are these objects interesting? Perhaps the most important reason is that they give a combinatorial understanding of Schubert polynomials in the study of Schubert varieties. And for me, at least, they also are interesting because they encode many families of interesting combinatorial geometric objects, such as triangulations, multi-triangulations, Nutamari lattices, and more. Okay. And my goal for this talk is to introduce first a Hopf algebra structure on these objects on pipe dreams, and then we will present on some applications. Are we good so far? Excellent. If there are any questions, do not hesitate to interrupt me. Okay, so what are Hopf algebras? So a Hopf algebra is, roughly speaking, essentially just a vector space whose generators can be multiplied and co-multiplied in some compatible way. And there is also something that is called an antipole. Now, one of the classical examples is the group algebra. So you take the vector space spanned by the elements of a group, and then you define some operations on this space. So one is the commultiplication and one is the multiplication. The commultiplication just takes an element of a group and split it in two. So G is split in G tensor G. And the multiplication of two elements G and H is just the multiplication in the group. So it's just G times H in the group, okay? And these Hopf algebras appear in many different places. So for example, polynomial rings, permutations, cohomology of Lie groups, Lie algebras, quantum groups, and many others, okay? So if you're not familiar with Hopf algebras, essentially what you have to do is to define two operations. And so let me give you an example of a very nice Hopf algebra, which is very simple to understand. So first, let's take the vector space generated by decks of cards. And for each generator, I need to tell you what the commultiplication and the multiplication is. And then this is extended linearly. So the commultiplication is an operation that takes an element and splits it into two, which are simpler. So it's very as simple as this. You have one deck of cards, you just split it in two, okay? Of course, this is not unique because you can do it at several places. So what you can do is just take the sum over all these possible pairs you get. Okay. Now, the multiplication is an operation that takes an element and creates, the multiplication is an operation that takes two elements and creates a new one. Okay. And the way I will do it is I just shuffle these two decks of cards. So you take two elements of your space, and then you just shuffle them. So you obtain a new deck of cards, and of course this is not unique. So what you can do is just take the sum over all possible ways of doing this. Okay, and this can be explained similarly in terms of permutations. So instead of decks of cards, let's take the collections of permutations of n. And you consider the vector space generated by all these permutations. And using these two operations, what Malvenuto, Rottenauer prove is that this has the structure of a graded Hopf algebra. Okay, and what are these operations? So again, so you have a permutation. So what you can do is to split this permutation in two. So for example, if you split here, on the left you have 3, 1, 2, and on the right you have the empty permutation. If you split between 1 and 2, then you get 3, 1 on the left and 2 on the right, and so on. Now, the problem here is that, of course, 3, 1 is not a permutation of n, so you just need to relabel the numbers so that it becomes a permutation. Just change the 3 by a 2 and the 1 by a 1, and that's it. So you just relabel all the numbers with the numbers from 1 up to k so that you respect the order. So this is the commultiplication. For the multiplication, it is also similar as we did with the deck of cards. So if you multiply the permutation 1, 2 with 2, 1, so what you do is you just shuffle these two sequences. So for example, this 1, 2 blue, 2, 1 red, or 1 blue, 2 red, 2 blue, 1 red, and so on. Of course, the results are not permutations. So what you can do is you just shift off all the red numbers by 2, and then you get all the numbers from 1 up to 4. And these two operations determine a graded Hopf algebra structure on this vector space. Any questions so far? Okay, excellent. Okay, excellent. Now, let me give you another example. This is a Hopf algebra studied by Lode and Ronco in 1998. And this is the Hopf algebra on the vector space spanned by planar binary trees. So binary trees are trees that look like this. So each node has 2 children. And in order to define the Hopf algebra structure, I need to tell you what the commultiplication and the multiplication are. So again, the commultiplication is an operation that takes an element and creates or splits it into 2. And how do you do that? So, well, you just look at a leaf of your tree, and then you just cut this tree into 2 smaller trees. And then you just say the tensor product of these 2 smaller trees. And this is not unique, so you just take the sum of all these pairs. Now for the multiplication, so you take two elements and then you create a new one. And the way you do it for binary trees is as follows. So first you split the second tree in as many subtrees as leaves in the first one. So in this case, there are 3. So you split this one into 3 smaller trees. And then you just attach all these trees on the leaves of the first one to create a new one. Again, this is not unique. So you just take the sum over all possible ways of doing that. Okay. And now what I want to do is to define a Hopf algebra structure on pipe dreams. And for that, I will also tell you what the multiplication and the multiplication are. Okay, so for the multiplication, given a pipe dream, I need to create or split it into 2 smaller ones. And in order to do so, I will first split the permutation in 2. So I will cut here, and I have a blue permutation on the left and a red permutation on the right. And then this 2, 1, 3 on the right is this 2, 1, 3 on the right over here. And this 6, 5, 7, 4 becomes 3, 2, 4, 1. Again, I'm just relabeling the numbers so that it becomes a permutation. So I'm doing the standardization of the permutation. Okay. And then what we will do is these red numbers here determine some red pipes. And then I will just contract these red pipes horizontally so that they fit into a triangular shape. And these blue numbers here determine some blue pipes. And then I will just contract them vertically so that they fit in a triangular shape. And this is not always possible. So in order for this to be possible, you need that these 3 numbers here, these 3 red numbers, are given by the numbers 1, 2, and 3. So if you will have a 4 here, this will not be possible because this will arrive down here. So this will not be possible. So we will cut an allowable cut if all the numbers on the right are less than all the numbers on the left. And this in combinatorials, this is often also called law and descent. Okay. So whenever I have an allowable cut, I can do these contraction operations, and then the multiplication is just the sum of over all these possible splits of these 2 pairs of pipe dreams. Okay. So that was very simple. So here's an explicit example. So for example, if I want to go multiply this pipe dream, so first I need to split the permutation. So here is when I split at the end, so I get the full permutation on the left, and the empty permutation on the right. I cannot split between 1 and 2 because 2 is not less smaller than 1, but I can split here because 1, 2 are smaller than 3 and 4. So this will be the 1, 2 here, and the 4, 3 become a 2, 1 here. And then I can also split the 4, which becomes a 1, and I can split at the very beginning, which becomes empty, and the 4, 3, 1, 2 permutation on the right. Okay. Excellent. Now for the multiplication, before I explain the multiplication on pipe dreams, let me re-explain the multiplications on decks of cards. So remember, in order to do it, so what I was doing is I take my 2 decks of cards and then I shuffle them. But in order to shuffle them, another option is I will split the second one as in many parts, in many smaller parts, and each of these smaller parts, I will introduce it in the first one at some place. So what I need to tell you is how this introduction or this insertion operation is. If I know how this insertion operation is, I just cut the second one in many parts and I insert them at several places. Okay. I will do the same for pipe dreams. So I will tell you what the insertion is on pipe dreams. So I want to insert this pipe dream, red pipe dream, in this blue pipe dream. So I will insert it here at some corner, and then I will extend the red pipes vertically on top and horizontally here on the left. And what remains, I will just fill it with the blue pipes from this picture. Okay. So again, so how do I default the multiplication? Then I just split in the second one in many parts, and then I insert them at several places. And this is how it looks like in this particular case. So for example, here I split the red one in 2 parts, then I insert them in different places. Okay. And the result is that these operations end up the vector space spanned by pi primes with a graded Hopf algebra structure. And this one is free and co-free. Okay, any questions? Good. Now, when you have Hopf algebras, one of the things you can ask yourself is, are there interesting Hopf subalgebras inside this Hopf algebra? And so let me give you some examples for this particular family. And the first one is, well, I will just restrict to the family of pi primes with some subfamily of permutations. And the permutations that I will consider are permutations which are reverse permutations. So they reverse the number. So n and -1 and -2, etc., 3, 2, 1. So these are the permutations that I'm interested in. And what we can prove is that this vector space generated by these pi primes forms a graded Hopf subalgebra. And this one is isomorphic to the Loder-Ronco Hopf algebra on planar binary trees. And the graded dimensions are given by the Catalan numbers. Okay. And this is actually very simple. So all you need to do is to do a bijection between pi primes with reverse permutations and binary trees. And the bijection is very simple. So you just replace each elbow. So for example, this one here by a node. So this will be this node over here. This elbow here will be this node over there, and so on. And then you just connect consecutive nodes in the same column or the same row. And this gives you a bijection between the two sets of generators of the two Hopf algebras. Okay, any questions? Okay, so let me give you one which is even more interesting. And in order to define this or to see this Hopf subalgebra, I need to tell you what a dominant permutation is. So a permutation is called dominant if its Rothe diagram is a Young diagram located at the top left corner. So what is the Rothe diagram of a permutation? So for example, if you have this permutation 3, 2, 4, 1, what you do is you just put a dot. So you just write like the matrix representation of this permutation. You just write a dot on the third row in this column, on the second row in this column, on the fourth row in this column, and on the first row in this column. And what you do is you just remove all the boxes that are either to the right or weakly below each dot. And then what remains is the Rothe diagram of your permutation. And a permutation is, so this will be the blue boxes here, and a permutation is called dominant if these blue boxes form a Young diagram, which is located at the top left corner of this square. Okay. And for example, Schubert polynomials of dominant permutations are easy or are interesting. Okay. Now, again, you can take all the vector space spanned by pi primes of dominant permutations, and this gives you a Hopf subalgebra. And the graded dimensions of these Hopf algebras are given by determinants of Catalan numbers. And the reason is because these dominant pi primes are in bijections with pairs of nested dict paths, which are known to be counted by this nice determinantal formula. Okay. So this is like the main Hopf subalgebra in which we are interested in this talk. So keep it in mind for the rest of the talk. So this is a nice moment to have a small break. If you got lost or got distracted, this is also a good time to come back to the talk. So I'm changing topic now.
I have a quick question.
Yes.
So what do you think of these pipe dreams? So you had this, so it's a permutation enriched by something, yeah? And in particular, what is this non-crossing, only twice crossing is allowed or something like this?
Yeah.
What should I think about here?
I do not quite understand your question.
So it's very vague. So you wrote down the axioms of a pipe dream.
Yeah.
And is there a different angle I can think about it? What it means?
I see. You mean an alternative description, which is perhaps more familiar to you?
Maybe, yeah.
No, that I know of at the moment. I have no another description, but essentially the reason why people work on this is because they were trying to find a combinatorial description of these Schubert polynomials. And when you do this, like you can, for each pipe dream, write a polynomial, and for the pipe dreams of a given permutation, so you can write down a polynomial from them. So this is what they are useful, and this is how people came out with this.
And is there a reason for this condition that the pipes are only allowed to cross twice, I think was the condition? Or is it deeply buried in this polynomial construction?
No, it is. So if you think about it, so there are like Coxeter groups, generalizations of this. And if you think in terms of Coxeter groups, what you want is like a reduced expressions of an element in a group. And the term being a reduced expression means that the lines do not cross twice. So this is a really, really natural condition in Coxeter groups.
Okay, thank you.
So this is really natural to us. Thank you. Any other question? Okay, so let's move on. So the second part of my talk will be concentrated on applications to multivariate diagonal harmonics. But before I tell you about the application, I need to tell you what multivariate diagonal harmonics is. And this is a beautiful story. This starts with the Macdonald positivity conjecture regarding the coefficients of the Schur's function expansion of Macdonald polynomials. So in the 1988, Macdonald was studying certain polynomials that are called Macdonald polynomials. And these polynomials are symmetric functions on some variables x1, x2, up to xn. And the coefficients of these polynomials are rational functions on two parameters q and t. And whenever you work with symmetric functions, this space of symmetric functions has a really nice basis, which is important in representation theory, which is the set of Schur functions. So each symmetric function you can expand in this basis of Schur functions, and then you get some coefficients. And somehow these coefficients tell you information about the representation. So these coefficients are kind of nice. And if there is some representation theory behind it, but in general, not. But so a priori, these coefficients are rational expressions in Q and T. And what Macdonald noticed is that these rational expressions are actually polynomials. And not only that, they have non-negative integer coefficients. And this became known as the Macdonald positivity conjecture. And if you are an algebraic combinatorialist and you see some polynomial whose coefficients are non-negative integers, then you get really excited and you want to describe this polynomial as some counting function. So you want to describe this polynomial as a counting function on some, let's say, objects, and these objects are counted with some weights. And Garsia and Haiman's combinatorial approach to this conjecture was to study a representation of the symmetric group of on certain Garsia-Haiman space. Now, so they defined the space and they started to make some computational computational experiments, and they noticed that the dimension of this space, so these spaces depend on some partition mu, and the dimension of these spaces is always n factorial independent of mu, and this conjecture became well known in algebraic combinatorics, and this was proven by Mark Haiman using techniques from algebraic geometry. And he does not only prove this conjecture, but he also shows that the representation theory behind this space is essentially encoded by this Macdonald polynomial. So you can describe these coefficients of Macdonald polynomials as counting multiplicities of the modules, of the reducible representations of these modules. So in particular, he proved that that the Macdonald positivity conjecture holds. Okay. Now, there is one special case of these spaces, which is if you take the partition mu equal 1, 1, 1, 1, and in this case, this Garsia-Haiman space is known as the space of harmonics. So what is the space of harmonics? So this one I can describe very precisely. So for this one, you first start with the set of polynomials with rational coefficients in n variables, x1 up to xn. So this is a polynomial ring. And then you take the ideal generated by symmetric polynomials or Sn invariant polynomials with no constant term. So what is an Sn invariant polynomial? Is a polynomial on the variables x1, x2 up to xn that satisfy that if you make a permutation of the indices in the variables, the polynomial remains unchanged. Okay. Now let me denote by delta of x, just the tuple of that is obtained by changing the variable x1 up to xn by the corresponding partial derivatives. Okay. And the space of harmonics is essentially a collection of polynomials in this polynomial ring, such that whenever you apply a partial differential operator that is coming from an element in this ideal, then this is equal to 0. Okay. And as Sn modules, this space can be seen as a quotient of the polynomial ring with the ideal. Okay. So you don't need to understand all the details in here, but one of the nice properties of this space is that this is a finite dimensional space. So, and the number of elements or the dimension of this space is equal to n factorial. Now, there is no reason to restrict yourself to one set of variables. So you can now extend this. So instead of having one set of variables x1 up to xn, you can extend this to two sets of variables. So now you have also y1 up to yn. And similarly as before, you take the ideal generated by Sn invariant polynomials with no constant term. So this group of permutations acts on this space just by relabeling the indices of the x variables and the indices on the y variables simultaneously. So this is a diagonal action. This is why this is called diagonal. And again, you do the same. So you just take the space of diagonal harmonics, which is the space of polynomials that vanish after applying these partial differential operators. And again, it's a fact that as Sn modules, this is isomorphic to a quotient of the polynomial ring with the ideal. Now, Garsia and Haiman started again to make some experiments with these spaces, and they noticed that the dimensions of these spaces are given by really nice numbers. So they are given by n+1 to n-1. This is a really common number in combinatorics. They count, for example, parking functions. And the dimension of these spaces is equal to this number. And this was proved almost 10 years later by Haiman using similar techniques from algebraic geometry. And not only that, so if you think this as a module, so representation theory of the symmetric group on these spaces, you can decompose this space into reducible components. And there is one particular part which is interesting, which is called the alternating component. And the dimension of this alternating component is given by the Catalan numbers. And this led to the now famous QT Catalan polynomials, which many people are excited about. Okay. And well, now, so we did one set of variables, we got n factorial, two sets of variables, and we got parking functions. You can go to more sets of variables, do it the same for 3 sets of variables, 4 sets of variables, and so on. In the trivariate case, Haiman made some computational experiments and he found these 2 really nice numbers. So the dimension of these spaces is given by 2 to the n plus 1 to the power n minus 2. And the alternating component is also given by a really nice product formula. And combinatorially, these numbers can be interpreted as the number of labeled and unlabeled intervals in some poset, which is called the Tamari lattice, which is a poset on Catalan objects. So you can see this as a poset on thick paths or on binary trees, any Catalan family. Okay. So intervals in this poset. Now, for 2 sets of variables, we will not talking about intervals, but elements in this poset. So it was given by the Catalan numbers. And labeled Catalan numbers are counted by parking functions, which was the n plus 1 to the n minus 1, which was in the previous slide. And well, no conjectural formulas are known for mod sets of variables. And one of the main difficulties to find these formulas is because when you make computations, large prime numbers appear. So there is not such a nice product formula describing these dimensions. Okay, so in summary, we have these nice families of spaces, which are called multi-diagonal harmonic spaces, which arise somehow from, or which are connected to representation theory. The dimensions of these spaces give you really nice combinatorial numbers. So in one set of variables, you got n factorial, number of parking functions, which are labeled Catalan numbers, and here labeled intervals in the poset of Catalan objects. And the alternating components have dimension 1 in one set of variables, Catalan numbers in 2 sets of variables, which are elements in this poset, and intervals in this poset for 3 sets of variables. So you might expect that if you go to, let's say, 4 sets of variables, you, instead of counting intervals, you will be counting triples, so chains in this poset, and so on. So in general, if you go to R sets of variables, you might expect that you are counting labeled and unlabeled chains with R minus 1 elements in the Tamari lattice, but this is not true in general. So there are more chains than the dimension of these spaces. Okay.
Cesar,
yeah.
By labeled and unlabeled, you mean isomorphism classes of intervals, or what?
No, unlabeled, I mean, unlabeled just means chains. So let me do it with intervals. With intervals, I just need intervals in the Tamari lattice. By label, I mean, if you think of this as thick paths, so you have 2 thick paths, and the second one is labeled, and it's labeled as a parking function. So you have some labels on the north steps, which are increasing vertically. So label means you have a tuple of thick paths where all the initial ones are not labeled, and the last one is labeled as a parking function. Does this answer to your question, Marcelo?
Yes, thank you.
Okay, good. Okay, so how the hell is this related to the Hopf algebra of pipe dreams? So let me go to pipe dreams. So as I told you, there is this really nice poset of Catalan numbers, which is called Tamari lattice. Pipe dreams also have a really nice poset structure, which is given by increasing flips. I don't need to tell so much about it, but there is a nice poset structure on these combinatorial objects, and you can also count intervals there. And the number of intervals in the graded dimensions on this. So what I will do now is I will only consider dominant pipe dreams, so the elements of the Hopf algebra of dominant pipe dreams. And the intervals in these graded dimensions is given by this sequence of numbers. And when you have a sequence of numbers as a combinatorialist, the first thing you do is you go to the online encyclopedia of integer sequences, you type it there, and then unfortunately this is not there. So you don't give up, you try to do something else. And we came up with this somewhat strange definition. So what I will do is the following. So these intervals happen to be in bijection with triples of dict paths in some way. And now what we will do is we will take tuples of dict paths with R elements such that every triple is arising from an interval in these dominant pipe dreams. So this is the second condition. And the first one is just that the first element is the bottom diagonal path. So it's the bottom dict path. And this is just for convenience. And then you start making some experiments. So for example, for n equal 4, you compute the number of Hopf chains of dict paths of size n equal 4, and then you get this sequence of numbers, 114, 68, 217, and so on. And then you get really excited. Why? Because if you go and compute the dimension of the alternating component of the space of diagonal harmonics for a fit n equal 4, and now you start changing the number of sets of variables, which is totally different to what was done before. So what was done before, you just fix the number of variables, let's say 2 sets of variables, and then you get these parking functions, the number of parking functions. Now we do something different. We fix the n, but now we modify the number of sets of variables, and then you get this sequence, which is exactly the same. And of course, this is not a coincidence. What we can prove is that for n less than or equal to 4, and any number r of sets of variables, the Qt Frobenius characteristic of this space of multivariate diagonal harmonics is given by a really nice formula. So it's a generating function that is counting Hopf chains, let's say with certain weights. So these weights are given by the LLT polynomials of Lascaux, Leclerc, and Thibault. And there is also some statistic on these Hopf chains that is accounting for the Q statistic. Okay. And when you restrict to R equal 2, this recovers the former shuffle conjecture for n less than or equal to 4 only, which was recently proven by Carlson and Mellit. And I do not want to say so much about this theorem, but what I want to say is that the important thing here is that is this Frobenius characteristic. And this Frobenius characteristic is an important tool in representation theory. So whenever you have a module, if you are able to compute the Frobenius characteristic of that module, then you get a lot of information about the space. Okay, so you get a straightforward corollaries from this result. And so, for example, you can compute the graded Hilbert series of the alternating component, and this is counting. So this is a generating function of chains with some statistics, some combinatorial statistics. You can also evaluate at t equal 1, and this gives you a Q Frobenius characteristic that is written in terms of elementary symmetric functions. But perhaps easier to understand is you get for free the dimensions of these spaces. So for example, the dimension of the alternating component is equal to a number of Hopf chains. And the dimension of the full space is the number of labeled Hopf chains. Okay. And this you get for free from that theorem. So this is these are some computations. So for n equal 1, 2, 3, and 4, and an arbitrary r. So this is the number of Hopf chains, and this is the number of label Hopf chains. And there is some magic happening here, which we do not understand. So there is a beautiful, beautiful conjecture by François Bergeron, that if you rephrase it in terms of this table, what you get is something like, if you take the alternating sum of these numbers here, so for example, 1 minus 4 minus 1, you get a 2. If you do it for this one, you get 1 minus 22 plus 56 minus 40, etc. If you do it, you will get a minus 5, and so on, and 14, and so on. So this is saying that the alternating sum of these coefficients here are given up to sign by Catalan numbers. And this is somehow, so this is quite mysterious, but this is somehow suggesting possibly that there is some topological space whose Euler characteristic is counted by the Catalan numbers, but this is still quite mysterious. Okay, now I should say that for n equal 5, the result is not true. So there is a small excess. We have a few possible candidates that kill this excess, but no real combinatorial rule to describe them, unfortunately. What we currently believe is that you can actually find the full multigraded Frobenius characteristic of these spaces as a nice formula, which is a sum over digpass of some multi-parameter generalizations of the LLT polynomials of Lascaux-Leclerc and Thibault, and some coefficients which are symmetric functions. So here is a small example, and these coefficients and these polynomials seem to have really, really beautiful properties, but this is still to be explored. Thank you very much.
Thank you very much for this nice talk.